Hey kiddos, and welcome to our last podcast. It's called Buffering Regions, Endpoints, and Indicators. A lot of the stuff is from Chem 20. It's pretty review-y, but I'm going to go over the things that are new especially, and just touch on the things that you already know from Chem 20. All right, so the endpoint is the observable color change. Remember, the endpoint and the equivalence point are about the same time. The equivalence point is the number of moles of each of the reactants that react with each other. In this case, we have an acid and a base, a strong acid and a strong base combo, right? So the pH at the equivalence point is going to be around 7, and the equivalence point is actually the number of moles of each of the reactant is equal. The endpoint is the time where, or at least empirically, where the color change of the indicator in the sample is permanent. And we have something called the buffering region, where we're going to talk about that. Again, the equivalence point is when the amount of acid and base are precisely chemically equal, and by chemically equal is the same number of moles, okay? So back in the day, they called these flat regions buffering systems. They still call them today, but for right now, this part here is a buffering region. The last flat part of the curve, the last part, is no longer referred to as a buffering region. And if you take a look at the buffering region, you'll notice that there's no real change in pH. It's very important that you realize that, or that you really accept that. There's no change in pH. If there is a change, some of you will be like, "Oh, but look, there's a bit of a slope to that line." Okay, there is, but for all purposes, that's so insignificant that we say that the pH here is maintained. Okay, that's the buffering region. It's maintained. So before any acid titrant is added, the sample solution is mostly water molecules and excess hydroxide ions. Because the sample, here's the sample, is a strong base. We're starting off with a strong base, right? So in that strong base, you have mostly water plus excessive hydroxide ions. Okay, buffering occurs because initially any acid that's added immediately reacts with the excess hydroxide and is converted to water. So as I'm adding like 5 milliliters, 10 milliliters, 15 milliliters of the acid, there's no change. It's pretty much the same, okay? And then at some point you reach the capacity. You reach the point where it's like after this, that one little drop of acid, all of a sudden there's a drastic change in pH. Okay, that's what all that's talking about. The equivalence point is approached as the excess hydroxide ions in the sample solution are almost all reacted with the added acid. So once equal amounts of the acid and the base are reacting, and you have a little extra of the HCl, there's going to be a drop in pH. It's actually going to go from 14 to all of a sudden around a 2. That's because it's tipped the scales. I've reached my capacity. Now that I add HCl, all my hydroxide ions are accounted, all my hydroxides accounted for. I can't chemically react with hydroxide anymore, so then I have an excess of hydrochloric acid or hydronium ions, and that's why the pH goes down. And this is, again, no longer called a buffering region, only here, okay? Now the solution consists of water molecules and excess hydronium ions once you've reached that capacity, once you've surpassed the capacity. When you're talking about indicators, bromothiamyl blue for this case for strong acid, strong base combo, bromothiamyl blue is a good indicator to use for strong acid, strong base titration because it changes color very close to the equivalence point. This orange 4 changes color way too low, and alizarin yellow changes color way too high, so they're not appropriate. An indicator is a Bronston-Lowry conjugate weak acid base pair formed when an indicator dye dissolves in water. So if you guys take a look, I'm going to talk about that for a bit. If you take a look at page 10 in your data booklet, you can actually go get your data booklet and take a look at page 10. It looks kind of familiar. We've had this kind of thing in chemistry 20. We didn't in chemistry 20 have a Ka value, but we definitely had everything else. Now let's take a look, for example, at let's take a look at phenol red. Take a look at phenol red kind of towards the bottom part of the table. And take a look at the suggested abbreviations. So the suggested abbreviations, and this is true for all of them, you'll notice on the left-hand side of the suggested abbreviations always starts with an H, notice that? And then your entity. In this case, phenol red, the abbreviation for phenol red is PR. Don't ask me why phenol red. I guess phenol P, R for red. So phenol red with the H in front, that means it's the acid form. That's your weak acid. And see how it's phenol red PR minus, that's your conjugate base form. So each of those forms has a color attached to it. Do you see that? So if it's yellow, the pH is 6.6 or lower. If it's red, the pH is 8 or higher. It doesn't mean that there's always going to be a high-low pH. Sometimes, for example, orange 4, if you take a look at orange 4, you have your weak acid and your conjugate base pair, the HOR for orange, and your OR minus, which is your conjugate base of the weak acid. And you see the range is only 1.4 to 2.8-ish, right? So just keep in mind that it's just talking about what's happening, what's tipping the scales. Is it the excess hydronium ions or is it the hydroxide ions? Okay, very important. So this equation applies for all the equations because IN just means indicator. And we're going to use colors red and blue just to kind of take a look at just very simple indicator colors, because you guys know that a red turns blue in a base and a blue turns red in an acid. Well, why? What's happening and why is it causing that to happen? What's going on? Let's break it down, okay, kiddos? An increase in hydronium ions. So let's take a look at our system. There's our system. And we see that there's hydronium ions in our system, okay? So an increase in hydronium ions present causes an equivalent shift to the left. It causes a shift to the left, producing more of the red colored acid form. Okay, so let's take a look over here. So I have my equilibrium. So there's my little seesaw. And I've added extra hydronium. Because hydronium ions are there, if I add more hydronium ions, it's going to tip the scale. I have to fix this. So in order to fix this, what I do is I have to add extra of the reactant. So that's why it shifts to the left. And then that's going to cause the seesaw to be level or to reach equilibrium. Now let's compare that to the addition of hydroxide ions. In the presence of excess hydroxide ions, in this particular case here, if you take a look at this system, there's no hydroxide ions. No, 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 no. So because we're adding something new that doesn't actually exist in the system, what's going to happen is that's going to indicate to you that it's the removal of something. So the excess hydroxide removes hydronium ions because it reacts with the hydronium ions to make water, right? In the presence of excess hydroxide, the hydroxide removes the hydronium, producing an equivalence point shift to the right. So what's going to happen is, for the second case, you're going to get this situation where you're removing hydronium ions, right? And in order to fix that, right, what you have to do is you have to add something to the right so that it becomes level or it reaches equilibrium. So it's just really important to know that the color change, right, actually is just indicating a shift. Is it shifting to the left or is it shifting to the right? Kind of cool, hey? All right, so polyprotic entities and sequential reactions. This you remember that here's my base, because I've dissociated my Na2CO3 into 2 sodium ions and a carbonate ion. This little guy is telling you that it's a polyprotic base. It's going to accept it can accept 2 hydrogens. And we see that with the titration curve because of these 2 vertical bumps. Typically, titration curves either look like this or they look like this, right? But here, there's one little vertical space and one little vertical space. There's 2 reactions. There's 2 reactions because this guy is going to actually react twice. It's going to accept a hydrogen 2 times. So the carbonate ion is a diprotic base because it can accept 2 protons, what we talked about. Hydrochloric acid is a strong acid, so it is like adding hydronium ions. So HCl is a monoprotic acid, only 1 hydrogen. If I compare that to sulfuric acid, notice that there's 2 hydrogens here. So this is a polyprotic acid, right? So for acids, you take a look at the subscript after the H, and for bases, you take a look at the charge. If it's a 3- charge, it's going to react 3 times. Okay. I think I say okay a lot. There's our first reaction, and there's our second reaction. No, there are no more reactions because at this point here, it cannot accept any more hydrogens or any more protons. So it's done. So nitric acid is a monoprotic acid, only one hydrogen. And sulfuric acid, like I told you, it's a diprotic acid, but you can say polyprotic. It's just more specific. It's not a big deal because of the two hydrogens, right? So remember, for every proton transferred by a polyprotic entity, the strength of the new acid or base entity formed greatly decreases. So typically, if I have something like this, H3PO4, if you remember this from Chem 20, it's going to react 3 times. The first reaction is it happens less than 50% of the time. The second reaction is less than 1%, right? The third reaction is about 0%. So even though it should react 3 times, the third reaction happens, I don't know, never. So we don't actually even show it in our graph. All right, so here's an example of exactly phosphoric acid, and notice that there's only 2 reactions. Now, really, it could react one more time, right? It could react one more time, but why bother? Why bother? Because here's our first reaction, and here's our second reaction. By the time we get to our second reaction, the third reaction will be 0, so we don't actually show it up. That's why, even though there's 3 here, there's only 2 bumps, okay? So as a general rule, only quantitative reactions produce detectable equivalence point in an acid-base reaction. So let's just summarize. Empirical pH curves provide a wealth of information, the initial pH of the sample, and the pH when excess titrant is added. So basically, it also gives you the pH of the sample and the pH of the titrant. It shows you number of quantitative reactions. So if there's more than 1 bump, we're dealing with a polyprotic entity. Non-quantitative equilibrium reactions, equivalence points for indicator selection, and it shows you the buffering regions. Remember, the buffering region is only the first horizontal line in the graph. So let's take a look about all the different combos you can have. You have, because you have access to strong acids, weak acids, strong bases, and weak bases. Typically, a weak acid combo with a weak acid, weak base combo, we don't use those because there isn't enough of equivalence points. So normally you're not going to see that combo. But let's take a look at the other combos. Strong base, strong acid. When you have a strong base, strong acid combo, what you notice is that the pH at the equivalence point, right, is always a strong base, strong acid combo. The equivalence point is always 7. And remember how you read the equivalence point? You take a look at the vertical space here, and it's the center of that. So here's a vertical space here. It's the center of that. So you can have strong base with a strong acid, or a strong acid with added to a strong base. Tongue twister. It has a large vertical portion. A wide range of indicators could be useful. Remember, when you're picking an indicator, anything here is a go. You want to get it, though, as close as you can to the center. You want that indicator to be as close as that as possible. Strong acid, weak base combo. So let's take a look at that. Any strong acid plus weak base, if we take a look at the pH at the equivalence point, is going to be below 7, which makes sense because you're reacting a strong acid with a weak base, okay? So equivalence point is always less than a pH of 7. And choose an indicator that changes color at a lower pH value. Example, bromocresol green, because it is going to change at a different pH than something like that has a pH of 7, for example. Equivalence point of a pH of 7. Here's a strong base, weak acid combo. So if you take a look at the pH at the equivalence point, you'll see that it's higher than 7. So equivalence point is always greater than 7. Choose an indicator that changes color at a higher pH value. And remember, it has to fit in within this little area here. So you don't have as many choices, but keeping in mind, you want it to change as much as you can to that equivalence point of where the pH shows in the center of the vertical space. So here we have a strong base added to a strong acid. Take a look over here. Well, about 7. Here's another 7. When you have a strong base and a weak acid combo, of course it's going to be higher than 7. And a strong acid with a weak base combo, it's always going to be lower than 7. Always, always, always. So here's some titration generalizations. Strong acid, strong base reactions are quantitative and have equivalence point of 7. Strong acid with a weak base combo, its quantitative reaction equivalence is going to be lower than 7. And a weak acid with a strong base, you're going to have a pH at the equivalence point higher than 7. Polyprotic entities, you'll see in the graph that it'll have 2 little bumpy bumps, not just one. So let's talk a little bit about a buffering region and what the heck is going on there. So as you know, here's our buffering region, okay? And because it's only the first one that counts, this one is no longer the second one. So a buffer, this is really important, kiddos. A buffering region is any combination of a weak acid with its conjugate base. So if I add 5 mils, 10 mils, 15 mils of my hydroxide, right? There's going to be no change. The pH is going to be maintained. There isn't going to be any significant changes in pH. That is your buffering region. That's what it does. And what does that is a weak acid and its conjugate base combo. So why is it doing that? If I add hydroxide to a buffering system, weak acid plus its conjugate base, here's your weak acid and here's the conjugate base, right? This is the conjugate pair. If I add hydroxide, the hydroxide is going to react with the acid. And it's going to do that for this region here where it's going to not change the pH. The buffer capacity is like, okay, I'm done. It's at the point where I have exhausted all of this. Like all of my hydroxide has reacted with the acid, for example. And then anything extra is going to bring the pH up. Okay, so it reaches a capacity. Everything has like a threshold where it's like, I'm done. Okay, if I have hydronium, if I add hydronium, a small amount of acid, it's going to react with the conjugate base. Okay, there's my conjugate base. And it too has a capacity, a buffer capacity. So after this point, obviously the pH is going to go down because then I'm going to have more hydronium. But a buffering system, remember, is this point here where the pH is maintained, it doesn't change. A buffer capacity is the limit of the ability of a buffer to maintain a pH level. So let's see a real life example. Blood plasma is considered a buffering system. Well, let's compare that to neutral saline. If I had neutral saline, which really is very similar in terms of like pH and conductivity to plasma, if I add a wee bit, like 1 milliliter of a strong acid to natural saline, it goes from a pH of 7 to a pH of 2 just by 1 mil. That's a dramatic change. However, blood plasma is a buffering system, weak acid with its conjugate base. If I add 1 milliliter of strong acid, 10 moles per liter, that's really strong, it's going to go from 7.4 to 7.2. Basically, the way we see it is that the pH is maintained. Does that make sense, kiddos? So blood plasma is buffered because the chemical reactions that take place in our bodies must be in a narrow pH. So basically the Bronsted-Lowry basically helps us understand excess reactions, titrations, buffers, polyprotic reactions, neutralization reactions, and indicator reactions. Bronsted-Lowry, they were a cool combo of gentlemen that totally changed our view of how we see acids and bases. It's just donating or accepting a proton. Who would have thunk it? It would have explained so many things. Okay, that's the end. Say goodbye to Chem 30. Have a nice day, kiddos.